and welcome to today's physics class. This class, we look at a topic called mirror formula. So let's look at mirror formula from start, and then we look at the several formulas for mirror. Then we have the concave mirror, convex mirror, and then we look at several important things to note in the study of mirror formula. First things first, notes please. Couple examples. Note. The focal length of a spherical mirror The focal length of a spherical mirror is related to its radius of curvature. I said the focal length of a spherical mirror is related to its radius of curvature by on the board please, F equal to F equal to R over 2. In other words, I can say that R is equal to F. All right. So if you're having your focal length and the rate of curvature, these two are related by F equal to R over 2 or R equal to F. That takes me back to when when I was solving problems under mirror. I saw a question there. It says, give the mathematical relationship between focal length and radius of curvature. I saw that question. So it means that the relationship between focal length and radius of curvature becomes what there? This one there. That F is equal to R over 2 or F equal to perhaps or R equal to F. This is the relationship between focal length and radius of curvature. Please note, please. Note, one line space paragraph, please. Note, when an object is replaced at a distance u, when an object is replaced at a distance u from a mirror of focal length f, from a mirror of focal length f, and the image formed at a distance v, and the image formed at a distance v, then they are related by, I said, when an object is replaced at a distance u from a mirror of focal length f, and the image formed at a distance v, then they are related by, on the board please, they are related by 1 over f is equal to 1 over u plus 1 over v. This particular formula here is a formula for a concave mirror. Why? A concave mirror is usually positive here. Why a convex mirror, it will be what the negative. I will explain that as we proceed in the study of mirror formula. So I'm saying this please. In quotes, the relationship between focal length, image distance, and object distance. The relationship is what you have here, right? By the way, I said this one is for concave mirror, please. For concave mirror, right? So before I move on, let's define term there. What's F? F is focal length. Next up there, I have U. U is called the image distance. Sorry, object distance, please. Object distance, and V is called image distance. Image distance. All right. Of course, all these things here are in meters. They are all in meters, right? So sorry. That's cm. It should be in cm, please. I'll give you why they are in cm. I'll show you why they are in cm. They are in centimeters, please. I will show you why they are in centimeters as we proceed. Centimeters, centimeters, centimeters. Usually, when it comes to when it comes to mirror optics, right? If it from experience and from practice questions, practice questions, we do observe that all these things are given in CM mostly, right? So they don't usually in physics. Whenever you see CM, we'll convert to meter. But in these topics, optics, mirror, all these concepts here, we use CM the most, please. That's why I said you use CM, CM, and CM. I have this one on the board. At this junction, please note. If I hear, please note. Note. The linear magnification in bracket capital M is given by the magnification in bracket capital M is given by, so now here the word linear magnification is M, and M is equal to V over U. That is, your V is for the image distance, your U is for the object distance. So magnification has to do with you first things first, place image before object. That's it. Anything that has to do with magnification is your ability to place image first before the object. That's the idea behind magnification. And I said this is its mathematical expression. By word, I have that magnification is equal to set V from here. If said V is what? Image distance. Of course, I have image distance. Alright, all over your U. Said U here is what? Object distance. I have object distance. This is your mathematical expression for magnification. Please don't forget the image comes before there, before object. Now, if you kind of try to ask me, what is the main definition of magnification? So put this down, please. Magnification is the ratio of the image distance. Copy that, please. Magnification is the ratio of the image distance to object distance, comma. It talks about how big or how small an object has been made. It talks about how big or how small an object has been made. Full stop, please. That is how you define um, linear magnification. So we have looked at relationship between focal length and radius. Done. We look at the relationship between focal length, image distance, and object distance, as you can see here. And I said this stuff here is an expression for what there a concave mirror. Haven't dealt with that. Look at linear magnification. It tells you how big or how small something is, and by expression, it means image distance for what there over object distance as shown on the board. Please, this is this in this case. But in terms of height, please. In terms of height, what would be the expression for magnification? Please note that magnification in terms of height is equal to height of image over height of object. So HI means height of image over height of object. So here's the idea. Magnification, you will always have image first before object. So in full form, magnification in terms of height, I have height of object, height of image per se, image over height of object, height of object. All right, this is your other expression for magnification, as you can see on the board. So you have this stuff here for the idea behind magnification, please. All right, so at this junction, let's look at 12 important bulletins. My goal is this. I don't want to focus on giving you notes definitions. Let's get the key ideas behind these things and move on. Literally. So I have taken my time to draft out 12, is it 12 or 15? I don't know, but when we start, please. I have drafted out some key important things you need to know as you study mirror formula, right? So I'll give them to you one after the other. So let's look at another important heading called Note the following. Please, heading, please. Note the following. Number one, an important heading. Please note the following, please. I'll give you, I think it's 15 or something like that. So let's just start this. Note the following, please. Note the following. All right. So note the following. Note the following, please. Number one, please. Number one. For a convex mirror, comma. For a convex mirror, comma. V is taken as negative in brackets minus. I said for a convex mirror, comma. V is taken as negative because a virtual image is formed behind the mirror, comma, focal length is also negative. Focal length is also negative. Alright, so that's number one thing to note that for a convex mirror, V is taken as negative. And I said why? Because a virtual image is formed. What's a virtual image? A virtual image is simply an image that cannot be caught on screen. I'll give you that later. Now what I'm saying is this. For a convex mirror, we said V should be negative. I have given you an expression for concave mirror. That's 1 over F equal to 1 over U plus 1 over V. That's concave. Now, from convex, we said that V should be negative. So let's say I'm having this place. So I'm saying this place. So number one, what we know before now is that we know that 1 over F is equal to 1 over U plus 1 over V. This man is for concave mirror. Now, when I said for convex mirror, that your expression becomes displaced. We said V is taken as negative. Why? Because a virtual image is formed. So I have that 1 over F for convex mirror is equal to 1 over U plus 1 over this V. We said takes V as negative for convex. We have minus V. In other words, plus times minus gives you a minus sign. So my expression for convex mirror becomes 1 over F is equal to 1 over U, minus 1 over V. This is your formula for a convex mirror. This one here is for concave mirror. Why this one here is for what there? For a convex mirror, as you can see on the board, right? And don't forget that we said U. This U is object distance, while V is image distance. Image U is object. V is image distance. U is object distance. V is image distance. Just try to know, like, differentiate them, please. I said U is object, while V is what the image distance as shown on the board. This is your first thing to know, that for a convex mirror, you have this expression. For a concave mirror, you have this one here. That's number one. Number two, please. Number two. So this is one I was trying to show you guys before. I was telling you that something is centimeter, other one millimeter. So I said this stops here. If you go and check past question properly, study past question most times, you will see that mirror formula, mirror optics concept there. They usually use cm for their unit. So put on please. Number two, for calculation involve optics. Is this number two, please? And listen all what I'm saying on the screen. In case you can't get me properly or you mistakenly had me wrong, Everything is, I'll take my time to edit this video. So they're on the screen. So likely pause the video and write them down. You understand what I'm saying? So number 2, please. For calculation involving optics, the focal length, comma, object distance and the image distance are expressed in cm, centimeter. So as I'm saying earlier now, I said for calculation involving optics, the focal length, object distance and the image distance are expressed in centimeter. As simple as this. I never knew this before, right? It took me time, Usually I do convert to cm to meters, but I later observed that these things are always presented in cm. Why am I converting? So go and make your research and confirm what I'm saying. So don't forget that we said for calculation involving optics, so the focal length, object distance, and image distance are expressed in centimeter. That's about 2 bulletin to note as a study mirror. Number 3, please. Number 3. The nature of the image produced by a convex mirror, please don't forget, a convex has negative, concave has positive. So saying this, please. The nature of the image produced by a convex mirror, comma, irrespective of the position of the object, from the mirror, the nature of the image produced by a convex mirror, comma, irrespective of the position of the object from the mirror, is virtual erect and diminished. Is virtual erect and diminished. What do I mean? All right, let's explain number 3. What do I mean by that expression? What do I mean? Okay, I said for a convex mirror, that convex mirror gives you a virtual erect and diminish, right? So for convex, so I'm saying that for convex, this creates a virtual erect and diminish. Hmm? Where? Oh, okay. Erect, of course, and diminish. All right. So we said for a convex produces something called virtual and move on to erect and diminish. So I will explain convex mirror properly now. Using 2 live examples. I'll use number 1. I'll use the shaving mirror to explain. Number 2. I'll use the mirror in a car. The one at the side of the car, right? So for number 1 there, let's try to explain convex mirror using a car. If you check a car properly, usually we have all been in a private car before, whichever one there. So if you check the car mirror properly, you see a description there. Huh? Yes, if you check a car, the mirror, let me just try to draw something out. Something like this. So that car, there's a description here. There wrote something here. For those that do notice very well, what's written there? There's a particular word that's always written under that mirror. What do you think it is? So, what do you think is written there? What will it be? Let me know in the comment section. What's written there? I want to get the answer to this, please. What is written? Literally, you're in a car, right? Some people just enter, they don't really observe a lot. So you should ask yourself, what's there? There is something written underneath that mirror. What do you say? Put on, please. So for those that don't know, please take note of this, please. Copy this down, please. Take note. Objects on the mirror are closer than the seems or look. Objects on the mirror are closer than the seems or look. What does it mean? It means that, please guys, let's be neutral. In a real life sense, if I'm coming closer to you, see the way I'm coming closer to my camera, I'm getting bigger. If I go far, I'll look smaller. So on a normal sense, for an Homo sapien means human being. So for a human being, on a normal sense, when something is small, it means that thing is far. When something is closer to us, it means that thing is no longer far. It's something behind us, right? Now they are telling you that objects in the mirror are closer than they look or seems. So it means that, don't go and say because the car behind you is small, it is far. No, it is not far. It's behind you. Why it looks small is because it was designed using what the convex idea. A convex helps you diminish something. Sometimes it's bigger. There's not to be bigger. It will diminish it. That's the concept. So if I have a camera this way, I can see like 5 cars that are behind me with my mirror. Why? Because my convex reduces, diminish everything to smaller thing there. So don't go and say that because my mirror, the car is small. It's small and I'm seeing it, so it is still far. Please, when you hit your brake, something can hit you behind. So there is this place. It is not far. The car is not far from you. It is because the convex mirror. That's why. So a convex mirror diminish something. So that's one scenario I can use to explain convex mirror for you. Number two is shaving mirror. Why shaving mirror? If you go to those old, I think in this century, we don't use shaving mirror again. What we go to barber salon that we do the cut there, right? We don't really shaving mirror, but those that can relate will relate. Those that can relate will relate, right? So if you check back your shaving mirror, you have your mirror this way, and then you have a shaving stick this way. The reason why we call it shaving stick mirror is because that mirror was designed with a convex idea. Why? Because normally if I look at my mirror, it should be showing me like it be showing something literally the way I look. But convex will reduce my face. Like my face will look small in the mirror. If I do like this, I'll be able to see everything. Literally, it will diminish that your face, something smaller, and then you'll be seeing everything. Literally, all your faces in that mirror. They can just please. Some people cannot relate. Anyways, that's by the way, please. So that's like the idea behind a convex mirror. The idea there is this: it diminishes. It's virtual, erect, and diminished. So this is how I can try to explain the idea behind note number 3, which says the nature of image produced by the convex mirror is irrespective um, of the position of the object irrespective of what of irrespective of the position of the object from the mirror. You can see that. So irrespective of the position of the object to that mirror, it will diminishing it will take it down. So it is virtual erect and diminished. So this is like the idea behind note number 3. Number 4, please. Number 4, please. Number 4. The magnification of a concave mirror. The magnification of a concave mirror. The magnification of a concave mirror can be lesser, equal to, or greater than unity. The magnification of a concave mirror can be lesser, equal to, or greater than unity. Why the magnification of a convex mirror? Why the mode there? Magnification of a convex mirror must be less than unity. Yeah. Now, please, you can hear the word unity, unity. If you are familiar with science term very well, unity in science term means one. So we are saying this for a concave mirror. For a concave mirror, the magnification, the M for a concave mirror can be either less than 1, greater than 1. I said can be what there can be lesser, equal to, or greater than 1. That's unity, greater than unity. So this one can be less than 1, equal to 1, or greater than 1. That's for concave. For convex, please, it must be less than unity. It must be less than 1. Hi, yeah, yeah, yeah. For listen, please, guys. Concave must be either lesser, equal to, or greater than 1, while convex must be less than 1. How can we apply this? So we said, please, the multiplication of these two for this one there, it must be less than 1, and that's true. If I have my camera here, let me show something, please. I don't think you can see what I'm doing, right? So this is my camera here. You can see my camera. You see, we have some what's it called? I'm coming. I have some number here. You can see the way if I increase my zooming, you can see. So we said for a convex mirror, that stuff must be less than 1. It means if my zooming is less than 1, is 0 point, it should become, if I show my face, my face looks smaller, right? So look at it, guys. I don't know how to explain this. Get it very well. Okay, let me just try to explain using some ideas, please. You know, on your camera, you have some readings like your zooming. This one, then like literally when you are zooming your camera, you see those numbers written 0.2. So yes, please. So the more I go backward to 0 point, no matter how I move less than 1, I then go beyond 1, I move less than 1, your camera will be going backward. But if I zoom it from 1 and upward, the camera comes closer to me, literally. So for a convex, we are expected to put zoom in the camera backward from 1 backward. So it was less than 1. And if it's less than 1 there, it means that your face will look smaller. You capture literally everything. But when you zoom it fully, for as concave, because concave can be lesser, concave can still be equal to 1, concave can still be more than 1. So whichever one there, if I zoom it off fully, it will show my face. Literally, it can even show only my nose. My face and my nose, because I have zoomed that stuff so much that it could only just see my face. That's for concave, please. For convex, please note that is what less than 1. That's what I want you guys to note as we proceed in our study of um, mirror formula, please. All right, so let's proceed, please. Where were we? Where are we? Okay, that's number 4. Number 5, please. Number 5. Number 5. The multiplication of a plane mirror is unity. The multiplication of a plane mirror is unity. Number 5, I said the multiplication of a plane mirror is unity. What's a plane mirror? A plane mirror is simply a mirror that does not either decrease your size or increase your size. It will present you the way you are. If I stand on if I have a plane mirror this way and I look like this, it will show me it will give me my exact height, the way I look plainly. Literally, it won't diminish or make me smaller or make me bigger. There are some mirror that when you stand on them like this, you will see your head up. Yes, there are some mirror when you stand on the mirror, like when you look at the mirror, you'll be seeing your head up. That's the kind of design that mirror has. For a plain mirror there, you see your exact height and your exact your body structure on the mirror, like without diminishing or increasing anything. That's like the idea behind a plain mirror. Number six, please. Number six, please. Number six. Number six. Convex lens is used to solve problem for far-sightedness. Convex lens is used to solve for problem of far-sightedness, comma. Far-sightedness, also called hy- hypermetropia, hypermetropia. Far-sightedness, also called hypermyopia, by bending the light ray we shorten the focal length, comma, making the light ray focus on the rectilinear retina in a proper way. Please, retina in a proper way. That's number six. Number seven, please, quick one. I'll explain six and seven now, please. Number seven, please, quick one. Number seven, please. Convex mirror or convex lens, please. Convex lens is used to correct the problem of short-sightedness. Concave lens is used to correct the problem of short-sightedness. In bracket, myopia. Alright, guys. So for number six and number seven, they look similar. One of them is far-sightedness. One of them is short-sightedness, right? So literally, this I have this place. For number six, there I said something. I said for convex. So a convex mirror helps you to solve a problem of a far-sightedness. So when I was in school back then, I had a problem identifying which one is short-sightedness, which one is far-sightedness. So I look at it, okay, is it in exam? Like, okay, differentiate between hypermyopia and myopia. Am I correct with what I'm saying? Hyper metropia and myopia. So what's the difference between the two of them? So I don't know which one is short-sightedness, which one is far-sightedness. So I get confused. But there's a way I later knew it so much that I can never forget. So the longer the word, it means far. Shorter the word means short. So hypermetropia, that spelling looks long. It means that thing there is for far-sightedness. While myopia is shorter in spelling, so it means what there it is for what short-sightedness. Those I could differentiate back then. I can remember, yes, those I could differentiate back then. I remember very well. So here's the thing, please. There are some people that cannot see properly. Like they have to like, okay, what's this? They have short-sightedness. They have to put in the camera and see, okay, what's today's date? Okay, today is 9:46 a.m. Okay, they have what there a short-sightedness. So most of them go and buy, glasses. That eyeglasses do well. Is it concave or convex? Content please. Those that have short-sightedness, when they look at phone like they're start saying they can't see easily, right? They'll go and get they'll go to doctors to get glasses, right? That glass I'm asking you now, is it a concave mirror or a convex? Or let's say convex lens or concave lens, which one is there? For me, what I give you now is what a concave lens, because a concave lens, as I said earlier, solve a problem for what there for short sightedness. So those that have short sightedness, they have to use a glass that makes things easier for them to look to see. It means that I'm using what there a concave lens. I'm bringing in concave design for the glass. That's the idea. That is the idea, please. That's how 2007 works, please. So if they ask you, hypermetropia is for the farsightedness, while myopia is for short-sightedness. All right, guys, almost done. Number eight, please. Number eight, please. Number eight. Number eight. The nature of the image produced by a convex mirror. Concave, please. The nature of the image produced by a concave mirror is real and inverted. Let me explain. I said the nature of image produced by the concave mirror is real and inverted. All right, inverted. Okay, right. Let's explain this. For number six, there. Number eight, I said once again. I said the image of the nature of image produced by a concave mirror is real and inverted. What do I mean? For a concave mirror, there. If I take a selfie if I take a selfie with us now, look at this. If I take a selfie this way in class, take a selfie. This thing here will give me my image the way it is back. It is virtual. It will give me back the image. But what there? Something will change. What do you observe? Let me check the production. Sometimes if you see my production now, before I just made a setting to it. Before it will not show my image here. It will flip it up, right? There's some things that you snap. When you snap anything and check, it will show in the other like you literally snap it with your right hand, but it will be as if you snap it with your left hand. If you should have experienced this before, right? That's the idea behind what we're talking about now. That the nature of the image produced by a concave mirror is virtual and what there? It is virtual and what there? It is real and inverted, right? So it is real and what they inverted at the same time. It will be as if you swap it to the other side. So let's say for instance now you saw a cloth. So let's say for instance I saw a cloth. I have a cloth this way. I have a cloth this way. And this cloth, what was here was DPG. DPG was on this cloth. If I snap this cloth with my camera, what I'll be seeing, I will not see DPG. I'll be seeing something like this. D like this. Then my P will be like this. And my G will be like this. Yes. So yes, something like it's what I put it. What's the English to use? Oh God. It will be as if you flipped it, like you flipped it. Have you experienced it? You should love it. There's no how. You've seen this before. Yes, you've seen this before. This is like the idea behind inversion or inverted, right? In last, I saw an exam. The man told them that they should write. I think year two students. They should write lateral in lateral inversion. We call this thing lateral inversion. Lateral inversion. So the man told them to write the word lateral. Look at this. Lateral. So this is the word lateral. The man told them to write lateral in lateral inversion. The way I wrote this thing this way, this is called lateral inversion. The man said they should write this word in lateral inversion. What will it be? Just flip them, right? So this L becomes this lateral inversion. A becomes A lateral inversion. T becomes T. But this E becomes this. This is your E. This E in lateral inversion. R becomes this. Lateral inversion. A becomes A and your L becomes this. This is lateral in lateral inversion. So when you take your camera and snap some words sometimes, It will be as if you snap the opposite side, and that's the idea behind a concave mirror. It gives you a real and what the an inverted stuffs, as you can see on the board. This stuff here is called lateral inversion, as you can see on the board. Let's number 9, please. Number 9. All right, number 9, please. Note, please. Number 9. Objects that does not allow light to pass through them are called opaque. Opaque. I said objects that don't allow light to pass through them are called opaque. Guys, back then, if I remember very well, I do call this thing opaque. Then, opaque. When you do self-reading a lot, you will not really relate to how those people pronounce words, right? I call it opaque. This is opaque, right? So any object that will never allow light to pass through them are called what there are called opaque. If I have my torchlight here now, if I put my torchlight here and I literally on my torchlight towards my phone, you can never see the reflection here. You can never see it here. It means this my phone is what there an opaque object. Why? It does not allow light to pass through them. So any object in the world literally does not allow light to pass through them are called what they are called the opaque. That's like the idea behind this. Example, we have wood, right? A wood is what? An opaque. Not just wood. There are many things there that are literally opaque. Anything that does not allow light to pass through them are called opaque. That's by the way on this. Continuation, please. Why objects that allows light, please? We are still on number 9. I think, yeah. Still number 9, please. Now I said, moving on, please. Why objects that allows light to pass through them are called transparent? Why objects that allows light to pass through them are called transparent? Obviously, when I'm transparent, it means you can see through me. So if I have, let's say, a white nylon, for instance, or perhaps let's say I have a glass, not sunglass, so you have a glass that is white, purely white. If I on light to it or put that light into the sun, you will see the reflection. Literally, it's transparent. So things that are transparent are called objects that are transparent, or perhaps objects that allows light to pass through them are what they are called transparent. Also, objects that allow some light, literally some light to pass through them are called translucent. So transparent allow full access. Translucent will not give you full access, literally. So we have opaque, transparent, and translucent. Opaque will never allow light to pass through them. Transparent will allow light to pass through them, while translucent will allow a little bit of light to pass through them. Example, please. Example. Example of opaque objects include number 1, wood, metals, and so on and so forth. Right? Example of transparent objects involve transparent objects. It means they can allow light to pass through them. Include water, hair, clean plastic, diamond, prism, and glasses, and etc. All these examples are example of what? Transparent objects. Why? They can allow light to pass through them. Example of translucent include frosted glass, tinted glass window. We have the sunglasses. All this one here will never allow light to pass through them. You literally remember when you go to beach, right? You wear some glasses, that sunglass. While you're wearing that sunglass and you look up, that light, the sun is not affecting your eye because that glass is what there is a translucent. It doesn't allow light to pass through them. That's why you can wear the glass easily. So that's like the idea behind transparent, translucent, and opaque. All right, so I have that done. All right, next up, please. Number 11. So number 10, please. Number 10. Number 10. Quick one, please. Number 10. Real image can be diminished from virtual image because real image can be formed on screen while virtual image cannot be formed on screen. That's number 10. Number 11, please. 11. When an object is placed at infinity in front of a concave mirror, when an object is placed at what there at infinity in front of a concave mirror, the image is formed at the principal focus, and the nature of the image formed is real, diminished, and inverted. Now, we are done with things to note. In our next tutorial video, we'll look at 12 good examples, 12 good past questions under mirror formula. We will solve literally 12 past questions under mirror formula. I will say I can apply all this formula and how you can use them in solving problems. Before I go, don't forget, for a far-sightedness, it's called what then? Hypermyopia. Mytropia. Yeah, mytropia. For a short one, there's called myopia. So I said to note difference. The longer the word, it means far sightedness. Shorter the word means short sightedness. And let me take you back to something. Let me just refresh your mind with something. There's something. Let me just show something. Please show some words. So I want you to leave your answer in the comment section of this video. So note something, please. Note. All right. So note this, please. Some optical defects of eye. Some optical defects of eye include number one. Let's say you have myopia, as we said earlier, for short-sightedness. Number two, we have the hypermetropia, right? Number three, let's say we have what we called strabismus, right? What we called um, sorry. All right, we have what we called, what's this one called? What do I call this one? Huh? B. Where is B? B. No. It's B here. Are you sure it's B? Are you sure it's B? B that is here. Are you sure? Okay. All right. We have presbyopia, and we have number 5. Let me call it astigmatism, right? So these are like optical defects of eye. I've explained these two. So make your research. These other two, give me a definition and leave your answer in the comment section of this video, please. All right. We'll see you in this class where we'll look at several past questions in the study of mirror. Please, if you miss it, you have missed all. Do what to check our next video on mirror formula calculations. All right. If you find this class helpful, the first time here, subscribe to this channel, leave a like, leave a comment, and share this video to your classmates. I said earlier, please do not always be selfish. This video you just watched, you learned a lot. Kindly go check the video. You see a share button there. Click on share, and for God's sake, share this video to your class groups. your WhatsApp community. Share it there, let them see it, so they can also benefit from this video, right? Don't just be only me all the time, only me all the time. Let other people learn also. Share the video to them so they can also watch the video. At the same time, also do well to check my description. See a link to my WhatsApp community. So you can join my WhatsApp community, WhatsApp channel, and WhatsApp group at the same time, where we have students over the world in the WhatsApp group there. So do it to join us, and then you'll be seeing my updates frequently in the group. At the same time, don't forget to please subscribe to this channel, and also follow my channel membership. So join our channel membership to have access to exclusive videos, right, of mine.